And welcome to a Climate Conversation podcast. This is a podcast series that we've developed to really be a complement to the documentary A Climate Conversation. And A Climate Conversation is the project of Walt Johnson. He's a geophysicist, and he really wanted to have a conversation, a Socratic method of going through and just questioning many of the things that we hear about climate. And Walt Johnson actually stepped up to the plate and decided to fund this documentary. And Walt Johnson, it's great to have you in this podcast series. This is really becoming something very informative for people, Walt. So welcome.
Thank you very much, Kim, and thank you to everyone else who've done so much to make this.
And our spokesman for A Climate Conversation is Dave O'Rourke. And Dave, you herald from Marin County, California. This has been quite the journey, as Zach had reached out to you, one of our producer, and said, hey, take a look at this documentary, and it's almost changed your life, right?
Well, it's made me a lot busier. I can tell you that. I've been living, sort of behind the Iron Curtain here in Northern California. California generally is not a place that encourages robust debate among, free-thinking individuals. And because I'm not a fan of hysteria generally, I've kind of had not paid a lot of attention. I own a Tesla, got solar panels up on the roof. I pay exorbitant taxes, but the weather's great. And that's about as much as I thought about it until I saw the movie and I challenged myself to learn more. And it's been a revelation to me. And I have met wonderful people along the way, including our guest today. I'm very excited to have him with us.
Well, and our guest for today is Dr. Lonnie Kennedy. And you can find him at Privateer Consulting Services. His education, he got his bachelor's degree from the University of Oklahoma in geology, his master's at Oklahoma State in geology, and then his PhD in civil engineering and environmental sciences at the University of Oklahoma, focused on biogeochemistry. Dr. Kennedy, it is really a delight to have you as our guest today. Thank you.
Thank you, Kim. It's really a pleasure for me to be here, and I'm so glad I got to make your acquaintances.
Well, this is going to be a very informative podcast. So, Dave O'Rourke, where do you want to start?
Well, I'm always interested in the background of individuals who join our podcast, and we've had a wide variety. Just so right at the top, let me encourage everyone to browse our podcast library. It now includes some extraordinary individuals in a robust, many hours total combined conversation about this incredibly important topic. We're talking about the biggest bill in history. This will eclipse all the spending that's ever been spent on anything ever to achieve apparently virtually nothing. I mean, in terms of achievement, if our goal here is to reduce the temperature of the Earth, it's a very difficult thing to do. It may not even be possible, as we have learned. So I want to encourage everybody to browse through our podcast, watch the movie again, share it with your friends. This is an important conversation. It might be the most important one we have when it comes to the treasure of our nation. So having started with that, Dr. Kennedy, probably very few people listening to this podcast know what biogeochemistry is. And I'm going to include myself, even though I've been trying to figure it out. What is biogeochemistry, and how can it inform our understanding of the Earth's climate systems?
Well, that's a good question. And my hat's off to Kim for saying it correctly the first time. So biogeochemistry is really looking at the interaction between microbes, in this case, microbes that are living, in my case, microbes that are living below the surface, so in the soil, sediments, and sometimes is very deep into the Earth's crust. but looking at how those microbes interact with their environment. So for a microbe, their environment is the sediment that surrounds them, and then the water that they're living in, or sometimes air that they're living in. Okay, and they are actually very active. So soil bacteria under certain conditions can completely change the mineralogy of the subsurface in ways that you don't think of. But in a broader sense, microbes, let's say microscopic life, has had a very important role in shaping the global environment of the Earth. So we may talk about this in a little bit, but as you know, as the planet evolved, the atmosphere of the Earth has undergone some very, very dramatic changes, and those changes are biogeochemical in their foundation. So just expand on it very slightly, so when the Earth was first formed, we had there was very little in the way of an atmosphere, and then we went through hundreds of millions of years of volcanic outgassing, and that volcanic outgassing gave us water and a lot of CO2. So early in the Earth's history, it was mostly water and CO2. And then we had some very creative bacteria that began to live at, say, some of the fumaroles that were in the oceans. And those bacteria could take dissolved minerals that were coming out of these fumarole and let's say like oxidized iron. And with the other chemicals that were in the area and heat, they were capable of transforming an oxidized iron into a reduced iron form. That's how they made their living. So they didn't eat other organisms the way we do. We think of that. They're literally living completely off of mineralization. Those bacteria filled the early oceans up with vast quantities of dissolved iron. And then shortly after that, we had a lot of CO2 in the atmosphere. Plants evolved. And those plants, of course, a plant will take CO2 and turn CO2 into oxygen. At that time, there was very little oxygen in the Earth. So the early photosynthetic algae were taking an abundant amount of CO2, and they began to turn that into oxygen. And so at that earliest process, when oxygen was first formed by plants, that oxygen combined with dissolved iron and reoxidized that iron back into an iron oxide, which precipitated down to the floor of the oceans and eventually gave us the massive iron deposits that we use today for our industrial purposes. So that was completely created by bacteria just doing their thing. And so eventually there was enough oxygen being generated that we had free oxygen in the atmosphere. And that precipitated another change where we began to have oxygen breathing organisms. And initially those organisms were soft shelled. And those organisms in the Proterozoic were capable of reproducing, and we had a wide variety of different animals, but they all had soft shells. And at a certain point, around the Cambrian period, which we'll kind of stop the dialogue at that point, but right around that point, organisms evolved so that they could have hard shells. Okay, and the hard shells that they evolved to use were basically created out of carbon dioxide that originally was in the atmosphere. Okay, so when life first evolved on Earth, we had probably 20 to maybe 30% CO2 in the atmosphere, and today we're sitting at about 400 parts per million, which is 0.004%. Okay, so there's been a dramatic shift in the Earth's atmosphere, and most of that has been frankly, facilitated by life. I assume, is that good enough?
Was a great beginning. Now, there's practical applications in the world for the work that you do. I wrote this thing down because there was no chance of me being able to remember it, but the biogeochemical reductive dechlorination, which
Oh,
don't
sure.
ask me to say that again because I won't be able to do it. But this is a fascinating process, and it sounds like it mimics much of these natural processes that created the Earth as we know it today.
Yeah, that's right. Yeah, so that particular process you're talking about, so there, one of the bad toxic chemicals that was spilled a lot in the past were chlorinated solvents. So the industry and military use widely for cleaning machine parts, getting oil off of it, and they are capable of taking oil off and getting it into water, basically. So they're very effective for that, but they are also carcinogenic. And a lot of that, in the past, they wouldn't let them put that in a sewer. They would, because it would destroy the sewer systems for municipalities. And so they had to get rid of it some way. And so they would just go out to a pit and dump these chemicals, the spent chemicals, into the pits, and they would go down, hit the groundwater, and spread. And they were a tough substance to try to clean up, and in part because normal bacteria did not want to touch them. So my process. So it turns out that you can go into the subsurface and you can supply what's called a labile organic, but basically a simple organic that microbes love to eat. So it could be lactose, for example, or sucrose, or a number of different things. Put that into the subsurface, and also in some instances supplement their environment with dissolved sulfate. So like Epsom salts. So calcium sulfate, you use it for amending your garden. And so the added sulfate that's added, there's a special group of bacteria. So we breathe oxygen, and a special group of bacteria, instead of breathing oxygen like we do, they breathe in sulfate. Okay, and so they're happily eating the organic, and to turn that into energy, they breathe the sulfate that you've supplied, and they breathe out deadly gas, which is hydrogen sulfide, which doesn't sound good on the surface, but that deadly gas doesn't stick around. It's very reactive, and it combines with iron oxides, which are very, very prevalent in most soils. So it will take a normal iron oxide, which another word for that would be like rust. So whenever you see soil that has a reddish color to it, or even a brownish color to it, that's usually an iron oxide. And it'll reduce those iron oxides so the hydrogen sulfide will combine with the iron oxide and create an iron monosulfide, which detoxifies the hydrogen sulfide. So now it's gone. And what you created is an iron sulfide. And as it turns out, these chlorinated solvents, when they come in contact with an iron sulfide, it strips all the chlorine off of it and completely detoxifies the toxic substance. And so almost all of this is invisible if you're monitoring the water. So you put in to the subsurface some organic matter plus some measured sulfate, put that in the subsurface. A special group of bacteria will operate. They will eat that up. It goes away. And they will modify to create brand new minerals in the subsurface. And those new minerals are like a filter. So when the toxic chemicals come through, it basically pulls the chlorine off of it and completely detoxifies the hazardous waste.
Well, let's see Dr. Mann try to do that. I think that might be difficult. But so speaking of that, if you don't mind, another foundational question, and then I know Walt and Kim have a lot of questions too, but maybe you can sort of give us a thumbnail of your understanding of the fundamental argument that's made by the UNIPCC, the Intergovernmental Panel on Climate Change, and the alarmism that accompanies that. And talk to us about it. What is the basis of their argument that we are headed for a catastrophe?
um, if you don't mind, before I answer that one question, I would just like to expound on my past just a tiny bit more, and that is to say that although I have worked in the environmental industry, a good portion of the work that I do is in the oil and gas industry. And what I tend to do is I take subsurface data and form that into a virtual representation of the subsurface. So I've done that all over the United States, and spent about 15 years working in Algeria. And so in addition to looking at certainly the environmental side of things and the biological side of things, I've also spent a lot of my career looking at the geologic side of things, both on the surface and the subsurface, which ultimately leads me to the opinions that I have today. Answering your question, that is to say, so the arguments that are proposed is that historically in the recent past, let's say starting at the 1700s, we had about 270 parts per million of CO2 in the atmosphere, which is considered a baseline. And then from 1700s, eventually getting up into the 1800s, that level stayed pretty constant. We were only burning wood as a society. And then we moved into the Industrial Revolution. And in the Industrial Revolution, that necessarily had to be driven by a more powerful source of energy than just burning wood or animal power or human power. And so we shifted over to mostly using coal for a long period of time. So you burn coal, you gain energy, but you also emit CO2. And so, of course, moving on in time, we started to discover oil and gas and the magnificent energy that it gives us at our disposal, and also sending more and more CO2 into the atmosphere. Okay. Coincidentally, with sending all that CO2 in the atmosphere, I mean, humanity has greatly benefited at the same time, bringing us to the point where we can enjoy this podcast from the luxury of our own homes. But the argument that's made now is that all of that CO2 that we've put into the atmosphere to bring us out of a very primitive state to the technological premise that we are at today, that has now poisoned the atmosphere. We're adding too much CO2 into the atmosphere. And what that will do, since CO2 is a greenhouse gas, that will increase the temperature of the Earth. And that temperature will ultimately result in a series of catastrophic events. So, unbridled global warming, runaway global warming, droughts. It's blamed for hurricanes and for tornadoes and for increasing the ocean levels and starvation, and it's a wide range of different negative effects that are pushed out there as being associated with burning fossil fuels. So that's the argument that's made. So Alex Epstein, who's an apologist for fossil fuel industry, I really enjoy his work. But his statement is that if you only look at the bad side of everything, and for oil and gas, that's all we do. So 99.99% of everything you see about oil and gas is negative. And if you really look at it, the positive aspects of oil and gas vastly outweigh the presumed bad things about oil and gas. And if you really focus in on the so-called bad things of oil and gas, you may find that those are really not so bad at all.
Well, in fact, I think it's possible to graph human flourishing side by side with the production of hydrochemicals or petrochemicals, excuse me. I think you may have a chart about that shows the expansion of use of these chemicals, these energy sources, with things like longevity.
Oh, exactly.
I think it'd be interesting for people to take a look at that and visually examine the connection between human flourishing and the sources of our energy. Well, there you go.
I guess you can see that. Good. So again, this came from Alex Epstein's book, A Moral Case for Fossil Fuels. So these are the charts that he shows in there. And the first chart, upper left, is saying, okay, well, here's CO2 emissions. And coincident with that, if you look at it, is life expectancy, population growth, GDP per person. These are all the positive things. And if you, again, look at the negatives associated with it, I don't think they're as bad as what the media portrays them to be.
Well, this is my idea of a hockey stick. Living 3 times as long with 8 times the money and a vastly increased number of women on Earth. Now, that's just speaking for me personally.
Exactly.
Those seem like good things. Tim, what do you think about that? Is this a good thing? What are we talking about with this whole climate thing? I wonder. Kim, do you have any thoughts about that?
Well, I'm sorry, I was waiting. I was thinking about your last comment. So
Sorry, we like to make the conversation lighthearted.
I definitely, I look at this and I cannot understand why we don't see the benefits of all of this and how it correlates. And I've recently been in different conversations with people that really are alarmist. They really believe that we're going to destroy the planet, and seem to be willing to change their own personal climates and their own personal prosperity. Maybe not so much, but they espouse that they're going to do that. And the amount of, really, I would say, propaganda is shocking to me. I was traveling recently and was at a beautiful place up in Sun Valley. And interestingly enough, and I have it right here, it has the whole report from Aspen, basically skiing company. It's Aspen One. It's their sustainability report. And I was just shocked at what I'm reading there. And ultimately, it would prevent human flourishing. And I'm just at a loss on it, Dave. I'm just really at a loss.
Well, Kim, we can be sure one thing, that there's a lot of disappointed people that Milton didn't wipe Florida out. There people find that there was a dozen deaths or something initially reported, and there are a lot of people disappointed by that. They wanted real destruction. The hurricane that just made landfall by Tampa.
Yeah.
There's a lot of people who see good news as bad news. So if it isn't destructive, there's been a bunch of craziness about this. I believe there were 17 more landfalling hurricanes that had greater destructive power in Florida since 1930 than this one. And yet the amount of hysteria surrounding this and connecting it to climate change was remarkable. It's a remarkable thing. So it's anti-flourishing.
It is. Yeah, I agree with that completely. The people simply do not understand what's being asked of them and how impossible that task is, and how little they actually have to fear. I mean, it's fear. The fear mongering that comes out of this is just horrific. This might not be a bad spot. If I let me advance just a few slides. Let's talk about this. So, you guys have certainly heard that having extra CO2 is going to cause the Arctic ice to melt, and that we are going to have sea level rise that will inundate large portions of the world, so on and so forth, right? This is a chart that shows the rise in sea level starting at the end of the last ice age. So around 14,000 years ago, which is not very long ago in geologic terms. From that point on, the Earth rapidly warmed in just a few thousand years. So people don't realize there was a mile-high glacier on top of New York City just a few thousand years ago. Okay, large portions of the United States, there was so much ice and snow covering just a few thousand years ago that it literally compressed the Earth. And as that ice has now melted, the Earth is still rebounding, coming back up to its unstrained state. And here in the last ice age, the ocean levels rose over 120 meters. Okay, so if you have a hard time converting, that's 360 feet roughly worth of sea level rise. It's huge. And what we see on this chart is that right here at this inflection point, where it had warmed enough to melt the ice off of a large portion of the world, and the climate warmed to the point that ice was gone, is when civilization started. Okay, and since civilization started roughly 8,000 years ago, and then here's the Industrial Revolution roughly in the 1800s. Okay, and then here we are sitting today. Okay, so you may look at that and say, well, that's quite a coincidence. It's not a coincidence. Humans were around, and when the climate finally gave us a chance to establish civilization, we did. Okay, and the thanks we get for pushing that forward to the technological heights that we have today, are people that basically want everyone to feel ashamed of the energy that we use every day to make our lives as good as they are. And the truth of the matter is that humans have never had it so well as we have today. Okay, this next slide. So again, this is just a composite of slides. I just pulled them from the internet. You can go look them up yourself. But this is a very nice one. So since the 1920s, this looks at the number of deaths due to climate-related disasters. And that actually looks like I've got that mislabeled at the top there, but that's climate-related deaths. So people dying from the climate have dropped dramatically. That's not because the climate's gotten any better. That's because we're using fossil fuels so that we can insulate ourselves from the harmful impacts of the environment that we live in. Same thing here is the number of tornadoes. I hear it all the time. I live in Oklahoma, which is the middle of the tornado belt. And we hear that all the time. Oh, yes, it's global warming. That's why we have so many tornadoes. They haven't really changed. The number of wildfires. So this one goes back, maybe you can't see that very well, but this particular chart goes back to the 1930s. So this goes from about 1930 all the way up to today. And the number of wildfires has gone down dramatically. Now, when people tell you the number of wildfires have gone up, they're looking at this little bit right here. Okay. And that little bit at the very end here is not because of climate change, it's because of forest management. So we've decided that we are not going to clear out the underbrush where we should and fight fires the way we used to, and that sort of thing. Let nature be nature. Okay, that's cool, but don't blame it on climate change. And then deforestation. So this is temperate forest. You can see going from the 1700s, getting up towards today. It's like, the amount of forest that we've cut down has dropped to virtually nothing. Okay, and the reason for that is we don't have to cut down trees for firewood. So we have cleaner sources of energy than going out and destroying the habitat. And then this one is tropical forest. And so there was a peak in that around the 1970s, but even it's going down. And what's happening is that, again, people used to have to go out and cut down the rainforest and burn it so that they could go out and grow crops in the fields. And, with fertilizers and, farming equipment and things like that, they don't have to do that anymore. And so it's protecting our forests. Same thing here, let's say with hurricanes. So that's, again, another thing. I mean, there's not really any change in trend associated with that. Are we having problems with drought or rainfall? And the answer is no. This is New Hampshire, snow cover just the same as it's been going back decades. But what has happened, if we look at food production, so food production has shot off the charts. Okay. Wow. Okay, from 1960, I mean, you are talking about more than doubling the amount of cereal yield that we get today. Well, how did we do that? I mean, did we double the amount of cereal yields because we went out and grew everything organically without using any chemicals or pesticides? Or no. We got that because we are using hydrocarbon to create fertilizers, and we're using mechanized tractors and harvesters to go out and get that food. We're using water more efficiently, and so across the board, the basic things, if you got a growing planet, you'd sure like to be able to feed them, and that's what the use of fossil fuels allows us to do. Another interesting thing that is that it's been estimated in several different sources that the increase in CO2 that we have seen since the advent of the Industrial Revolution has actually improved agricultural produce by 20%. Okay, that's not considering fertilizer or considering the mechanization. That is literally plants need CO2 to survive, and we live in an environment today where we do not have enough CO2 to really allow plants to flourish in the state that they evolved in, and consequently, plants don't produce the way they should. And as we have added more CO2 to the environment, plants have been able to grow much healthier, much faster than what we've had in the past. And people have said it was accused that climate change was going to desertify the planet. So we'd have, with heat, we'd be having rolling deserts, and that's not true. You can look at this on satellite imagery, and you can see actually that the rims of the Sahara are greening. So there's green that's now pushing its way into the Sahara, and not the inverse. And satellites can easily scan the entire planet, and they show that, especially in the last 10 years, that the planet has greened. Okay, and that is due to the extra CO2 that we've added to the planet. So not only did we pull ourselves out of poverty by using fossil fuels, we have also made the planet green. So if you want to look at a true green energy, fossil fuels is the way to go.
So, Dr. Kennedy, a couple of things. First of all, alarmists have gotten very wealthy on being alarmists, and we've seen reports of them buying beachfront property in New England. And if they really believed that the oceans were rising, they would not be buying that beachfront property, right?
I wouldn't. Yeah, I mean, that's exactly right. They don't believe, even though they give lip service to it, they don't believe it. And I would say that many of the people who do say that they believe in global warming, deep down in their soul, they're not that concerned about it. Okay, and why do I say that? So an example was not long ago, I was listening to a Harris rally. And again, this is not meant to be political, just an observation that during her rally, she said, and we will fight against climate change, and make sure that we put policy in place to fight climate. And everybody cheers. Everybody, yay! Climate change is real and existential, and everybody starts to applaud. Well, how about if I told everybody in the room they had cancer? Okay, I mean, if you really believe that climate change was a truly existential threat and we're all doomed, I assure you wouldn't applaud. But they do. It's the idea of something that we can all rally around and call our own that really excites people.
So, and Dr. Kennedy, as we are recording this, we've just gone through North Carolina has experienced Hurricane Helene. I flew back from Wyoming yesterday, and the smoke was so thick in Jackson near the airport from the forest fires there. So when you say that the hurricane's intensity isn't that different and that forest fires are not that different, the news out there seems to say something different. So what do you say about that? What do you say to people?
I say this, which is you will note that every single time somebody stands up and says climate change is real because of some event, the challenge is show me the data. And I assure you they won't have it. Okay, I'm telling you that there is no significant change, and I'm showing you the data to back it up. Okay, it's a statement that's made for whatever purposes, personal, political, and maybe you even believe that, but still go and look at the data.
Okay. Walt, what you have created here and with this whole podcast series, I know that you were really thrilled to have Dr. Kennedy on. And as Dave and I were listening to you and Dr. Kennedy in the preparation on this. You had some really interesting conversations. Your studies are you're a geophysicist. So what's the next thing that you think we should talk about?
So I would like to shift subjects very slightly. So to this, which is, my argument is, and I think if you look at the data objectively, you will see that the fears that have been pushed out amongst the public about climate change are unfounded. So I will make 2 points to that. One of them is that they are unfounded, and if there are any changes to climate that may occur through the use of fossil fuels, by using fossil fuels, we are easily capable of managing those problems. Okay, if we didn't have fossil fuels, those problems become very, very big. So, like, we've got hurricanes that have blown through recently, and we have the energy infrastructure to go out and rebuild and reduce the amount of human loss of life and power, and everything is coming back to these areas. It's a tragedy every time it happens. But we have the infrastructure and we have the energy to be able to go out and mitigate those problems. Whereas if the same thing had happened, I don't know, in Indonesia or Africa or places like that, it would be a tragedy. I mean, many more people would be dead. People,
Right.
Would die of disease, malnutrition, no clean water. Okay, we don't worry about any of that stuff here because we have the energy infrastructure to be able to handle it. Okay, and then you say, what is driving this? If you can look at the data and it says there's really not much of a problem here, then why is there such noise about climate change and the disasters it will bring, and why is the government time and time again creating programs which will cost trillions of dollars and give virtually no benefit at the end of the day? And what's the driving force behind that? And you take out the data, as we've already shown, you keep throwing the data. It's not really this, it's not really that. Okay. And by the time you get all focused in, what it boils down to is these charts right in front of you here. Okay. And those charts, so all the squiggly lines that you see in the center there. So on the y-axis, that's theoretical temperature in Celsius, going from 0, meaning a baseline of 0. So basically what the climate was, say, back in 1975, the temperature was. And then all of those squiggly lines that you see in there are computer models. Okay. And if you look at those computer model simulations, and this one's going all the way up through, I think it goes through 2022. And if you look at these model runs, one after the other, you see that they are all predicting very high temperature changes in a relatively short amount of time. Okay. And then if you look just below all the squiggly lines, what the dotted line in the center there is the average of all of these different computer simulations. Then the bottom line there is the actual temperature that we've seen going from 1975 to 1920.
Wow.
So during that time frame, 1975 to 2020, the temperature has theoretically gone up by about 0.6, maybe 0.7 degrees Celsius. Okay. But the models predicted that it would be going up at 1.5 degrees Celsius. It's just okay. And and the truth of the matter is that we started off in the 1700s with about 270 parts per million CO2 in the 1770s. So around 270 parts per million in the 1700s. And today we're about 400. So we've come up about 180, get that to my head, 30 degrees, parts per million, okay, over that immense time frame. Okay. And then the temperature increase. So if you do go back to the 1700s and consider that a baseline, our temperature has gone up about 1.1 to 1.2 degrees Celsius. Okay, that's very manageable. That's not something that we should necessarily be all excited about. But what these guys are trying to do is to predict the future, and categorically, every single time they've tried, they have 100% failure.
Wow.
Okay? So these models is what's driving the decisions of the IPCC. It's driving decisions that are made in various governments around the world. Are these models? It's not reality. So we don't suffer any of these supposed consequences today. And what we're doing is we're using these charts as a guide for what the future is going to be. So you talk to somebody that's living in London. I was in London not too long ago, and the cabbies in London are just going, it's crazy. I mean, we're not going to be able to drive our cabs in downtown London. They all have to be electric, and we can't afford them, and you can't park a gas powered car any place in town. It's this sort of draconian stuff that's going on. And it's all based on these charts, which are flat wrong. They say it's wrong. Okay. And on the flip side, which is really getting into my purpose for being here. So on the flip side, these charts are looking at the future. And as a geologist, what we usually do is look at the past. And so that's kind of my purpose for being here is geologists also create models that look at the past. And what does the past tell us about the role of CO2 and temperature? So if we see in the geologic past that indeed increasing CO2 leads to catastrophic global warming, then I say, okay, your arguments are well-founded. But if we look in the geologic past and see that's not the case, then it really kicks the wind out of the basic concept that we're arguing about today.
Wow. So Walt, what's your thoughts on
Well,
this?
if we go back to that chart we were just talking about, if we
So
could.
sorry, I'm going to do it right now.
Sorry.
Busy while I'm flicking around.
Yeah, there. We had Lord Monckton on not too long ago, and he was looking at those charts, and his comment was most of the people were not using proper feedback in doing their calculations. But there's one group that did use the feedback, and you notice that group, which is at the bottom, and it kind of almost follows what we observe.
And which group was that? Do you remember?
It was the Russian group.
There you go.
Which is strange. And he had talked to them at length about what they were doing and approved of the way they were doing their model.
That's right. Isn't that interesting? So the one group that has nothing gained by pushing up the temperatures is the group that's the most right.
And also the Russians are not joining in the Paris Climate Accord either.
So there's a there's another topic. We've been exploring it in the last several podcasts, which is, roughly speaking, it's in the category of cost and benefit. Like, we're contemplating spending staggering amounts of money on this problem. And what we've been discovering on the benefit side, particularly with Lord Monson a couple of weeks ago, Walt, showed calculations that were predicting, and this was science. I mean, I don't ask me to repeat the calculus here, but I was convinced after watching it, something on the order of 7/1000th of 1 degree Celsius, and banded around that were other responsible calculations that showed a very similar and equally sort of, tiny changes that might be affected. But you have a slide that I think is very effective. I hope it's in your deck today, that shows, sorry, I've got the sun right on me, that shows what we're asking wind and solar to replace. You have a chart of available energy. Here you go.
I think that's a good, I mean, this is reality slapping you in the face. So at the bottom down here, so this is over time, starting at 1800, going all the way up to 2023. This information is showing, it's Our World in Data. I wanted to make sure they got credit for this. And so this is showing different types of energy use, basically in the world. And so here you go. So at the bottom down here in brown is traditional biomass. Okay, so that is, for the majority of the world, not the majority, a large portion of the world, that's still true today. They are burning wood and cow dung to cook their meals, okay, which is an absolute travesty that we in the modern world do not reach out to people like that and bring them up. But in fact, we're talking to them about doing the opposite. I mean, we're sending emissaries to tribal countries where they are indeed still burning dung to cook their food on, and telling them that's the way to go. That's the future. Just stay here and don't emit any carbon and we'll all be fine. Okay. But then you can see here, starting back in the 1800s, we started using coal. The coal is still pretty high, and then above that, oil. Okay, so I mean, you think about this. So I mean, coal, that's the Industrial Revolution. Oil is our entire transportation system that allows us not only to go from place to place, but also to move food from one place to another. And then natural gas coming in on top of that, which is predominantly used for industrial purposes and heating our homes. Okay. And then you see up here nuclear power in green, hydropower in blue. And you would think that, certainly nuclear power could be accentuated without generating any carbon. And ultimately, that's what we do. Hydropower used to be very popular, but the environmentalists killed the concept of building any new dams because it disrupts too much of nature. And then you have wind, which is that teeny tiny little spot right there at the top. Okay, then modern biofuels and some other renewables. Okay, on solar, solar, you can barely see it, is right inside here. So the plan is for us to take these two little pieces that are up here at the top, and we are going to replace everything that's down here except biofuel, traditional biomass. We're going to replace all of that in a decade or two. Okay.
There's a couple of interesting things about this as well, which is if you created a similar chart that showed the amount of land use required by these energy sources, what would this chart look like? And you would see nuclear invisible, right? Biomass would be the same as it is. Nuclear takes nothing. The hydroelectric projects take They're on the rivers already. You can use ocean wave technology and other things, but wind and solar are extraordinarily land use heavy. And so
Exactly.
you would see land, land use for wind and solar here, and for everything else, tiny. So that's
So
one. And I'd love you to talk about that, but I'd also like you to talk about availability of the materials that are required to create these alternative
mhm.
energy infrastructures that we're talking about.
Uh, I would like to interject that for me personally. So I live in the country in the Arbuckle Mountains in Oklahoma, which is, and I live probably a half mile from probably the biggest scenic tourist area of the state, okay, which is Turner Falls. So there are many hundreds of thousands of people that come every year to this area because of its natural beauty and hiking trails and all that kind of good stuff, right? And yet, I mean, exactly at the park here is where they put in windmills. Okay, so now you stand and you look. If you look straight ahead, you can see this like 75-foot waterfall cascading down. And if you turn your head 5 degrees to the left or right, you see gigantic windmills on the mountains on either side.
Wow.
It's gas. I mean, really horrible. And I mean, this is outside of my field of expertise, but basically, they're very intensive, all of these. So all of those technologies are very mineral intensive. So you're going to be going out and digging up a vast amount of minerals to make windmills and solar panels. And then the problem is you've got to store the electricity some way. And that is just completely impractical. You can't do it so far. I don't see any technologies on there down the pipe that would be able to do that. And because of that, solar and wind basically operate at about 30 to 35% efficiency. So they only operate about 35% of the time.
Wow.
So they run when the sun is shining and when the wind is blowing. And the rest of the time, they may be, we may have favorable conditions, but if the wind is too high, they have to stop. And if they do generate electricity, we can't store it. And so it's just wasted. And so that's what you get. And then it's only useful in our electric system. We can't easily put it in our cars. Or any type of anything that we would use for transportation. I mean, they're trying to make a run at it, but it's not very practical the way things are today. So it's a boondoggle. I'm sorry, it's a boondoggle. That's all there is to it.
If I could inject one thing on that chart we have, I was fortunate to live with great grandparents, and hearing the stories of all these people on what life was like collecting cow pies to cook on, what life was like when they later got coal to use, and what life was later as they got propane to use. Life quality was always improving. No one wanted to go back to cow pies.
I wonder why. Yeah, well, and I've heard it said, which is correct. You can't really see it here, but wind and solar, okay, they actually do go all the way back here to the 1800s, right? So I mean, that's how we moved our ships was with wind. Okay, we're using solar to grow our plants with, and use as fuel. So I mean, they go all the way back, and it's like we have spent over 200 years trying to get away from wind and solar. Okay, I mean, trying to get away from wind and solar and biomass. Okay, and now we have a group that says that's the only way that we can go in the future, is by wind and solar. So they're trying to push us back to here. And the idea is we'll use technology to make that more feasible, but it's just not feasible at all.
Well, and life was tough. Walt, my grandmother grew up on the plains of western Kansas, and they had to get buffalo and cow dung to heat their homes and cook on. And she said as a little girl, she learned the difference between a frozen cow pie and a dry cow pie. There's a difference.
You learn fast.
You learn fast, yeah. So, Walt, you've really had a vision for a climate conversation. What you've created has been really amazing. And these conversations of these podcasts with amazing experts like Dr. Kennedy, I've learned so much, and I know listeners are as well. What else do you want people to know as we have Dr. Kennedy on this podcast?
Well, I've been asking everyone what is going to be the benefit if we go to net zero. And I always get a very small number. I think Lord Monckton said it would be 1/10 of a degree. And Clauser said it would be none at all, that clouds would act as a thermostat. So we're putting a lot of resources into something that will not benefit us as a society, it seems.
Definitely. And Dave, jump in here. What else should we talk about?
Well, there's a fascinating. I did a little homework about this, and I'm a big fan of Dr. Kennedy. And in looking at the correlation between temperature and CO2 concentrations, and over geologic time, discovering that there's not a sort of reliable correlation between temperature on Earth and concentrations of CO2, greenhouse gases in the air. But there is a correlation that has been demonstrated, and that's between ice cream consumption and drowning deaths. I don't know if you have that slide where we can demonstrate that as ice cream consumption goes up, more people drown. There you have it.
That's it. Yeah, so I heard this in some podcast sometime in the past, and I actually looked up the data. The guy that brought this concept was, what he's trying to get at is the idea of causation. Cause and effect. And so what he mentioned was that there's a very good correlation between eating ice cream and dying by drowning. And I thought, well, that's interesting, And so if you look at that and you see, well, yeah, it's true that the more ice cream that people eat, and that's measured down here in terms of dollars of sales of ice cream, assuming no ice cream ever goes to waste in our house. So I assume when we buy it, we're going to eat it. So anyway, you can see, that goes up. Well, it's a decent correlation, 87% R-squared correlation, so it's good. And what the deal is really is that when I first look at this, my mother was right. She said never eat and go into water after you take crap and you drown. But in fact, what it is that during the summer, people buy more ice cream, and during the summer, more people go swimming. Okay, and so at the end of the day, it's true. Okay, but the two don't, they don't really correlate. There's a third factor that's involved that's causing both of those to change together, right? That is part of what you need to think about when you're talking about the relationship of CO2 to rising temperatures. Okay, is the CO2 causing the increase in temperatures, or is the increase in temperature causing the CO2, or both? Is possible, right? And a big part of the puzzle that people don't understand with respect to CO2 is that the Earth is a giant incubator of life, and all non-plant life, virtually all non-plant life is emitting CO2. Okay, and microbially, there's a vast amount of microbes and organic matter that's stored in the soil, and these guys are really what's responsible for turning that back into CO2. Okay, and bacteria, the bacterial decomposition of organic matter is strongly related to temperature. So I'm not sure if I actually brought that. I don't think I did. But you can demonstrate in any laboratory that as you increase temperature by 10 degrees, you double the amount of microbial activity that's going on. So as the earth warms, you will automatically generate more CO2 out of the system. And you will also generate more methane because some of the decomposition of organic matter is done by methanogenic bacteria. This is not exactly the slide. Yeah, so if you don't mind, I'll jump to this point, which is really getting into the reason why I knew. This is the carbon cycle that your mother taught you. And this is the nice and gentle one, where just like we were talking about. Plants are taking CO2 and they're sending off oxygen. Animals are getting the CO2 and growing biomass and bugs and whatever else in here, and then they die. And mostly bacteria are responsible for turning that dead matter back into CO2 that goes to the plant. Okay, so that's the standard carbon cycle, but this is much closer to the real carbon cycle, and this is a scary carbon cycle. And so the carbon cycle we just looked at is this one up here, little animal eating plants. Okay, everything's going along very nicely, right? But that's not the real carbon cycle. The real carbon cycle is that over here off to the edge, you can barely see it, is that you have mostly in the oceans, but it's sometimes on land as well. So in the oceans in particular, you have CO2 that's in the air, and then different types of animals are taking that CO2 out of the air. So either to build their bodies with or to build their shells with, they're taking the CO2 out of the air. So let's take a shell, seashell. There's CO2 in the air. It dissolves into the water. A seashell takes that. By the time it's in the water, it's bicarbonate. They take that and that CO2 and convert it into a limestone shell. Okay, but once they've converted that and turned it into a limestone shell, there's a very good probability that shell is not going anywhere. It's going to lay in the ocean, and there's going to be more sediment dumped in on top of it, and other shells are going to grow, taking CO2 out of the air. Okay, when that CO2 is taken out of the air, it's gone. Okay, the only way that CO2 that becomes part of the ultimately the sediment of the earth, the only way that CO2 winds up getting recycled is that by tectonic plate movement. You have a plate that's sliding along, and that buried material eventually gets to, in general, it's going to be the point of plate collision, where you wind up with some subduction, and that plate gets shoved down, heats up, turns into magma, and goes back out through a volcanic vent. Okay,
Fascinating.
that's the only way that CO2 comes back.
Wow.
Now, we'll see in just a minute. But so, we'll look at this over geologic time. But you can see that what's happening here is that a vast amount of CO2 over geologic time has been pulled out of the atmosphere and added to the strata. Okay, I just read a report today where they claim to have figured out how much is coming out by volcanic activity, and it's around 0.3 gigatons per year. Okay, now to give you, that's 0.3 gigatons per year, and to give you a reference, the total amount of CO2 that was generated by burning fossil fuels in a year is approximately 32 parts per million. Okay, so you're talking about 2 orders of magnitude greater or less, I should say. So volcanoes are not really doing their job. They're not cycling CO2 back in the atmosphere where it could be used. Here's the problem with that. I'm going to skip just a little bit here. And I did have this. The problem with that, I'm going to skip quite a bit just because it flows. Okay, so here is a chart that was put together by some guys on the internet. They did pretty good, actually. I went back and verified the data on this. And this guy, Richard Scotis, again, has done a remarkable job here. So what we're looking at here is geologic time. And the black line represents a geologic model. Okay, so this geologic model is telling us an estimate of CO2 over geologic time. Okay, so the CO2 is being read over here on the y-axis, and that's going from 0 to 8,000 parts per million. Remember, today, we're at that little red line down here at the bottom, which is 400 parts per million. Okay, and what you see, a little bit before, I told you about how Earth's atmosphere formed and how it was driven in large part by life on Earth that actually drove the ancient atmosphere. And we stopped kind of all the way up to about this point. So, photosynthetic plants had evolved, multicellular life had evolved, and, had pulled CO2 originally was about 20 or 30% in the atmosphere. So through those eons, it removed all the way down to less than 1% CO2 in the atmosphere, which I believe is 10,000 parts per million. Okay, so, and then we start off the oldest of the Paleozoic era, which would be the Cambrian period. So, and that's about 600,000 years ago. So the time scale is here at the bottom, I should say. So this is today at 0, and we're going back in time to 600 million years ago. Okay, so very far back. And so when we start at this point in the scale, some interesting things start happening. So, and over geologic time, what you see is CO2 going down, 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 down. It actually crashes here, then it rebounds, and then it goes back down again and crashes again. And this is where we're at today.
Wow.
Is at the very end. Okay. And so, doing simple math here, you can say that we have lost 95% of the CO2 that God gave us to run a planet with. Okay. And where did that CO2 go? Okay. That's the question. And here's the geologic answer to that, which is this. I actually call this interval in here, I call this the first carbon crash. Okay. And so we start off in the Cambrian period, and as geologists, we know what happened in the Cambrian period. So prior to the Cambrian period, life was mostly soft, so like jellyfish and chitin and things like that. So very soft forms of life that are not very well represented even in the geologic records. But starting in the Cambrian period, marine life figured out how to grow a hard shell around its body. And so what animals started doing is, like we kind of talked about before, is there was CO2 in the atmosphere, it dissolves into the water, and then these animals figured out how to take that CO2 in the water, combine that with calcium, and create a calcium carbonate shell, okay, a hard shell. And when those animals died, a lot of those shells just dropped to the bottom, and the next layer gets dropped on top of that, and the next layer gets dropped on top of that, and the next layer gets dropped on top of that. And so we had some massive deposits. My house is sitting on a massive deposit of limestone that came from the Cambrian era in the Arbuckle Mountains. We have here, we have limestone deposits from this period of time that are 14,000 feet thick.
Wow.
Okay, 14,000 feet. I mean, you can imagine layer by layer of animals taking CO2 out and building their shells, adding it all up, and then eventually getting up to 14,000 feet. And these deposits, though not as thick as they are here, extend over large portions of the continent. Okay. And so what you see from the geologic record, and this is from geologic model. Okay. So the geologic modeling is telling us that in this period where life evolved to generate shells, our carbon in the atmosphere dropped from 7,000 all the way down to about 3,000 parts per million. Okay. So a massive amount of CO2 dropped out of the system and was converted into a lot of it into limestone. Okay, then the next epoch that we get into is the Silurian and Devonian. And here again, you see that CO2 levels got pulled down dramatically again. Okay, so they got pulled down to not about 1,500 parts per million. Okay, and what was going on here is that the source rocks for a large part of the Earth's oil and gas system were deposited here, okay, during the Silurian and Devonian. So the major source rocks in the United States come from the Silurian and Devonian deposits. And so basically these are very large anoxic seas where there was a lot of chlorophyll bacteria that were growing on the surface, dying, photosynthetic bacteria dying and then falling down to the bottom and being preserved. So again, it's that process of their bodies falling down and getting incorporated into mud deposits. But that, that reduced the CO2 in the atmosphere from about 4,000 all the way down to 1,500 parts per million. Okay. Then the next period hit, which is, we call it the Carboniferous. Oh, I wanted to mention something too. So on these, this prior slide here, a couple of them. So, back when we were talking about limestone, so, I mean, you take a cubic meter of limestone, so roughly a 3 foot by 3 foot by 3 foot cube of limestone. It takes 288,000 cubic meters of air with CO2 in it to make 1 cubic meter of limestone. Okay, the point is you suck the CO2 out of a vast amount of air, and it's locked up in a solid mass of limestone. And the same thing is true when you look at source rocks. So from what I know of the source rocks, the amount of organic material it takes over 372,000 cubic meters of air with CO2 in it to create 1 cubic meter of source rock. And then the next epoch, which is the Carboniferous, we call it the Carboniferous because there's so much carbon that was deposited during this time period. So this is the time period where the major coal deposits of the world were formed. And a thought for this is that, so prior to this time, plants were mostly soft-bodied plants like ferns and things like that with couldn't gain much height. But at this point, plants evolved lignin. So lignin is what makes a piece of wood hard and stiff. And so that allowed trees to grow upright and become very tall trees. But it is theorized that when those things fell down, there was no organism that had evolved to the point where it could degrade those tree trunks. Okay, so that's mostly done by fungal, by types of fungus, and they had not evolved to the point where they could degrade down lignin, which is a tough thing to break down even today. Okay, and so basically, we had several 100 million years where plants were taking all the oxygen out of the air. They would fall down dead into the swamp, tree after tree after tree after tree, creating these massive deposits of coal that we have in the world. And you need 1.7 million cubic meters of air to make 1 cubic meter of coal.
So, Dr. Kennedy, so for a novice like me, what you're saying, I think, is that we've had over all these, thousands, millions of years, that all of these plants have died and been on top of each other. So it would be I would say, naturally occurring fossil fuels that when we use those, then we are releasing all of that's been buried for so long. Would that be a correct summation or not?
I'm glad you thought of that. So that is exactly correct.
Wow.
And if you think about it, okay, so as a petroleum geologist, we go into an oil field, and the most that we could generally hope to get out of an oil field is about 30%, sometimes higher, but oftentimes about 30%. So we're leaving 70% of the oil in place. We can't get it out. Okay, it's just there, it's stuck. Okay, and that's only the oil and gas that we can get it. Okay, and this is just a wild guess on my part, but I would say that of the total amount of oil and gas deposits we have probably in the world, so the total amount of carbon that's locked up in those formations is we've probably gotten out maybe 5%, maybe less than that. Okay.
Wow.
So in saying so, we have only put back 5% of the carbon that originally came out of the atmosphere in the first place.
Goodness. Well, this has been really fascinating, Dr. Kennedy. Walt Johnson, geophysicist, what's your final thought that you'd like to mention regarding all of this information?
I'd like to go to that ice core graph he had of temperature and CO2 at one time.
Yeah, at my only point in this is to say that we are sitting right here today at the bottom, right? So we have 400 parts per million CO2, and in the geologic past, it was thousands of times, 20 times higher than what it is today. And I mean, we're talking about when dinosaurs ruled the earth, right? I mean, the biota was very, very, very prolific. So I don't think we're in any danger of adding a few more hundreds of parts per million to the atmosphere. Okay, and I mean, it's not going to cause us anything but good. And from my perspective, we are far closer to having too little CO2 in the air today than too much.
Wow.
Okay.
Well,
and if we
yeah.
forget what Walt was asking, so see if I can get all the way down here. Here, one of these guys. Where I'm at now. There we go. This is a good one.
Yeah. Yes, that's basically throughout what we call the ice ages. I mean, we're in a little period of warm spot in the middle. But you notice whenever the temperature goes up, the CO2 goes up. And we get back to the causation doesn't mean correlation, or correlation does not mean causation. And a lot of people will look at that and say, yes, somehow we did something to cause a lot of carbon dioxide, and it warmed up everything. But in reality, that has shifted a little bit. When the earth warmed, the oceans would warm, and CO2 comes out of the ocean like you do in a soda when you put it on a table and let it warm up. It comes out of the oceans, and we increase the CO2 because we warmed. And so a lot of times when we notice we're getting warm, and also the CO2 has also increased. So some of this is not man causing all the CO2. A lot of it is natural.
Wow.
So,
Gentlemen,
let me explain it really quickly. So, the bottom scale here is time, so it's years before present, and this is coming from Vostok High School. So the data is public; anybody can plot it out. So this is going from 0 years back to 450,000 years ago. And the ice core data is probably pretty sound. So I think we've done a good job with it. The orange line is CO2. The blue line is temperature. Okay. And you clearly see these spikes over geologic time. And what you should see is you should see CO2 going up, okay, and then temperature going up following the CO2. Okay, that's the theory of today, right? In saying that, that's not the way you read this chart. So the oldest is here, and we're getting younger as we go to the left, right? And so time and time again, these are ice ages. I'm sorry, these are ice ages, and these are interglacial periods where it warmed up, okay, without man. Okay, and what you see is that temperature and CO2 rise together, okay, up to near 300 parts per million. And then for some reason, temperatures start going back down and CO2 lags behind. If CO2 is making temperature, then you would have to see CO2 going down first and then temperature, or at least going down at the same time. Okay, but they don't. It's just the opposite. So all of this CO2 generation and temperature generation that you see occurred tens of thousands of years before man. This is all purely natural. And what's happening is, in fact, it's Milankovitch cycles that are driving this. And so the Earth is naturally, because the orbit of the Earth, eccentricity, and those sorts of things, the Earth goes through a period of warming. And as the Earth warms, mostly microbes start ginning up, and they start generating CO2. So life on Earth in general, when the temperature rises, life on Earth rises with it. Okay, and then as temperatures fall, then gradually life on Earth is gradually falling off over time. Okay, so what this is telling us is that adding CO2 is a good thing, not a bad thing. And although man does add some CO2 to the atmosphere, you can show that a large portion of the CO2 and almost all, I would say, of the methane that everybody's crying about are coming from natural sources on Earth. But it's not humans burning fossil fuel. It's Mother Nature doing her thing.
well, Dr. Lonnie Kennedy, this has been
Thank you.
fascinating, and thank you for all of this information. This has been great. This is a really informative podcast, and we thank you very much for that. So thank you, Dr. Kennedy. And Walt, your final thought?
I think we've covered quite a bit in this journey, but thank you to everybody. And this is all very important. Thank you.
And I think Dave O'Rourke, something I learned was the ice cream and drowning deaths, causation and correlation.
Yeah, I think maybe this global conversation that's happening largely without us about catastrophe and suffering and is got the accent so badly on the wrong syllable that it's hard to know where to begin, because we bring impressive scientists on board for these conversations. Again, I want to encourage everybody to go through our podcast library. If this is a topic of concern to you, educate yourself about it. And I make a bold assertion here that this film and these podcasts contain more thoughtful and well curated and truthful science-based information about this topic than any other single resource that you will find. And the result of learning what we've learned should be a joyful conclusion that we're moving to a better place than we've been in before, where our focus can move from alarmism to the end of energy poverty. If you can take a minute and be generous in your spirit and consider what the end of energy poverty could mean for 1 billion people around the earth, it'd be the greatest gift that we could give them. And you saw the graph that correlated the use of these fuels, these naturally occurring fuels, with longevity, with population growth, with flourishing humanity. That's all true. You don't have to wish it into being. It's proved. So maybe it's time for people to lighten up a little bit, stop canceling each other, and remember that we're really part of the reason we're put here is to have a good time.
So, gentlemen, thank you so much. And again, please
Thank
check
you.
out acclimateconversation.com. You can watch the documentary there as well as this amazing group of podcasts. Dr. Kennedy, thank you so much for sharing all of this with us. We greatly appreciate it.
That was definitely my pleasure. Thank you so much, guys.
Walt, Dave, until next time.
Thank you.